Hello everyone, welcome to the next section of the course, selecting the right model with hyperparameter tuning. This section will introduce the important concept of model selection, allowing a comparison across ML algorithms. You'll learn how to tweak the hyperparameters of ML algorithm using cross-validation and grid search in OpenCV. Now we move on to the first video of this section that deals with evaluating a model. Let's get started. Model evaluation strategies come in many different forms and shapes. In principle, model evaluation is simple. After training a model on some data, we can estimate its effectiveness by comparing model predictions to some ground truth values. Let's begin with evaluating a model in the wrong way. The reason we never evaluate a model on the training set is that, in principle, any dataset can be learned if we throw a strong enough model at it. A quick demonstration of this can be given with the help of the iris dataset. So we'll load the iris dataset using scikit-learn. By executing these 3 lines of code, we'll import numpy as np and store all data points in matrix X and all class labels in the vector Y. Next, we'll choose a model and its hyperparameters. For example, let's use the KNN algorithm, which provides only a single hyperparameter, that is the number of neighbors, k. With k equals to 1, we get a very simple model that classifies the label of an unknown point as belonging to the same class as its closest neighbor. We'll instantiate KNN with these lines of code. Then we'll train the model and use it to predict labels for the data that we already know. Finally, we compute the fraction of correctly labeled points. On executing, we can see an accuracy score of 1.0 as an output, which indicates that 100% of points were correctly labeled by our model. If a model gets 100% accuracy on the training set, we can say that the model has memorized the data. But is this truly measuring the expected accuracy? Have we really come up with a model that we expect to be correct 100% of the time? As you may have gathered, the answer is no. This example shows that even a simple algorithm is capable of memorizing a real-world dataset. Further, let's evaluate a model in the right way. A better sense of a model's performance can be found using a test set. When presented with data held out from the training procedure, we can check whether a model has learned some dependencies in the data that hold across the board or whether it just memorized the training set. So, we'll split the data into training and test sets using the familiar train-test split from scikit-learn's model selection module. But how do we choose the right train-test ratio? Is there even such a thing as a right ratio? Or is this considered another hyperparameter of the model? There are 2 competing concerns here. If our training set is too small, our model might not be able to extract the relevant data dependencies. As a result, our model performance might differ significantly from run to run, that is, if we repeat our experiment multiple times with different random number seeds. As an extreme example, consider a training set with a single data point from the iris dataset. In this case, there would be no way for the model to even learn that there are multiple species in the dataset. If our test set is too small, our performance metric might differ significantly from run to run. As a result, we'd have to rerun our experiment multiple times to get an idea of how well our model does on average. As an extreme example, consider a test set with a single data point. Since there are 3 different classes in the iris dataset, we might get either 0, 33%, 66% or 100% correct. A good starting point is an 80-20 training test split. However, it all depends on the amount of data available. For relatively small datasets, a 50-50 split might be more suitable. So we'll execute it with this code snippet. Then we'll retrain the previous model on the training set. After that, when we test the model on the test set, we suddenly get different results. Here we see a more reasonable result, although 88% accuracy is still a formidable result. But is this the best possible result? How can we know for sure? To answer these questions, we have to dig a little deeper. Selecting the best model. As you can see here, the regression result of 2 different trees, one with depth 2 and one with depth 5, fit into a sin function. Looks like this. It should be clear that neither of these fits are particularly good. However, the 2 decision trees fail in 2 different ways. Here, the model is said to have high bias, as the model does not have enough flexibility to account for all the features in the data, Such a model is said to underfit the data. The other decision tree model has high variance, as the model has so much flexibility that it ends up accounting for random errors in the data. You can see that on the right-hand side of the graph, where the blue curve, thin line, would jitter a lot. Such a model is said to overfit the data. Fundamentally, selecting the right model comes down to finding a sweet spot in the trade-off between bias and variance. Let's return to the KNN algorithm and the iris dataset. If we repeated the procedure of fitting the model to the iris data for all possible values of k, and calculated both training and test scores, the generated result will look something like this. Let's unpack the diagram. From this diagram, we can gather that there are three regimes in the model complexity landscape. So the first regime is, for very low model complexity, a high bias model, the training data is underfit. In this regime, the model achieves only low scores on both the training and test set, no matter for how long we trained it. Next, for very high model complexity, the training data is overfit, which means that the model predicts the training data very well, but fails for any previously unseen data. In this regime, the model has started to learn intricacies or peculiarities that only would appear in the training data. Since these peculiarities do not apply to unseen data, the training score gets lower and lower. Lastly, for some intermediate value, the test score is maximal. It's this intermediate regime where the test score is maximal that we're trying to find. This is the sweet spot in the trade-off between bias and variance. This means that we can find the best algorithm for the task at hand by mapping out the model complexity landscape. So that's all about evaluating a model.